Welcome to Simple Physics. In this session, we are going to see about entropy and probability, the relation connecting entropy and probability under statistical thermodynamics. There will be a net increase in entropy of the system under an isolated system when it undergoes an irreversible process. So for all irreversible process, the entropy of the system increases. Already we have studied this in the earlier class. So for all reversible processes, the entropy of the system increases. So what is this isolated system? So isolated system means the system does not interact with the surrounding, but the energy of the system remains constant. Such a system we are calling that as an isolated system. So when an isolated system undergoes an irreversible process, there is a net increase in entropy of the system. And some examples of irreversible processes we will see. All spontaneous processes, just like spontaneous expansion of gas, spontaneous division of one gas into another, all comes under the category of irreversible processes. For all these processes, the net increase of entropy as well as the probability, or which is otherwise called as randomness, that also increases. Okay, so both the entropy as well as the probability increases for a system when it undergoes an irreversible process. In 1896, Boltzmann derived a relation between entropy and probability. You know that entropy is a thermodynamical quantity and probability is a statistical quantity. In the equilibrium state, it is observed that both the entropy and thermodynamic probability have their maximum value. That is, entropy is maximum as well as thermodynamic probability, that is also maximum if the system attains an equilibrium state. Okay, using this observation, so this observation gives an idea to Boltzmann, and Boltzmann derived a relation called Boltzmann's entropy relation, which is nothing but a relation connecting entropy as well as a probability of the system. S represents the entropy, K is it is the Boltzmann's constant, and W is the probability, or in other words we can say number of microstates in a given system, that is represented as W. So relation connecting statistical quantity as well as thermodynamic quantity, such a relation we are calling that as Boltzmann's entropy relation. So this expression S is equal to K log W. Now we can derive this relation using Boltzmann's idea. Now we will see about the Boltzmann's entropy relation, that is a relation connecting entropy and the probability, that is called as Boltzmann's entropy relation. According to thermodynamics, the function, that is the entropy of a system, which is represented as S, is related to temperature as 1 by T is equal to dou S divided by dou E. E is the energy of the system, S is the entropy, and T is the temperature of the system. In this way, the entropy as well as the temperature can be related to one another under thermodynamics. So take this as equation number 1. But according to statistical mechanics, parameter beta is introduced. Beta has the dimension of reciprocal of energy. So the thermal energy, which is represented as kT, so beta is equal to 1 by kT, and rewriting this as 1 by T is equal to K beta. Just I am cross multiplying the terms and obtaining the expression for 1 by T. 1 by T is equal to K beta, where K is the Boltzmann's constant. And already we know the expression for this beta parameter. Beta parameter can be written as dou by dou E log W. E is the energy of the system and it remains constant in all irreversible processes. And W is the probability, or in other words we can say this is number of microstates of a system with energy E. So we can also call this W as probability or randomness, or otherwise number of microstates of a system with the energy E. The energy E remains constant in the case of an irreversible process. And from 1, so 1 by T is equal to K dou by dou E log W, and from 1, so 1 by T is nothing but dou S by dou E. So using equation number 1, we can rewrite this equation number 2 as dou S by dou E is equal to K dou by dou E log W. So I need the relation connecting S and W alone. So once again I'm integrating. To eliminate the differentiation, I'm integrating on either side with respect to energy term. Okay. So when we integrate this expression, we will get the final result as S is equal to K log W. S is the entropy of the system, K is Boltzmann's constant, and W is called as the probability or randomness, or in other words we can tell that as number of microstates of a system with energy E. So in this way, Boltzmann derived a relation connecting entropy and probability of a system. Boltzmann's entropy relation, as we have derived, is S is equal to K log W. From this expression, it is very clear that as entropy increases, the value of W, that is the thermodynamic probability of a system, that also increases. Since S is directly proportional to log W, as entropy increases, the probability, the thermodynamic probability of the system, that also increases. Okay, now we see about the statement of theorem of equipartition of energy. So the statement is very simple. The average energy of a system is equal to half kT, where K is Boltzmann's constant and T is the temperature of the system. So in a statement, just I read this. For every degree of freedom in a system, in thermal equilibrium at temperature T, the average energy of the system is half kT, where K is Boltzmann's constant. Okay, so the important point to be noted is the system should be in thermal equilibrium at a particular temperature T. And for each degree of freedom, the average energy, if you calculate, the average energy comes as half kT. So that is the statement.